So number one, we're going to find all the values of x, y, and lambda such that del f equals lambda del g. What we do is we actually find del f and del g and multiply del g by some lambda. We don't know what it is to begin with. And we set corresponding components equal. And we get a system of equations, the solutions to which, x, y solutions to which, are those points, x naught, y naught, where you could possibly have extreme values of f on the constraint curve. And we're going to evaluate f at those points from 1 to find the absolute extrema of f under the constraint. In other words, we're going to call those points critical points. Sound familiar? Remember critical values from Calc 1? We're going to call those points critical points. And we plug in all of our critical points. The way I've set up the problems in the homework, if you evaluate the critical points in the function, the biggest one is going to be the absolute max. The smallest one is going to be the absolute min when they exist. In other words, Lagrange multipliers doesn't guarantee, this method doesn't guarantee the existence of extreme values. So in this example, it says find the extrema of f of xy equals 2x squared plus x plus y squared minus 2 on x squared plus y squared equals 4. So there's two ways to look at the constraint. You could think of this guy as g of xy equals the constant 4. However, it would be safer if you subtracted 4 from each side and got 0 on one side, so that you had x squared plus y squared minus 4 equals 0, and you think of x squared plus y squared minus 4 as g of xy and 0 as your constant. That would be a little safer, because you need to be in the habit of getting all the variables on the same side. If you forget to do that, you're not going to have the right g. Okay? Obviously, 4 is not a variable, but if you get in the habit of doing that, if you get in the habit of setting it equal to 0, you'll never make that mistake of not bringing a variable to the other side. Okay, so this is it, guys. Del f is equal to lambda del g. What you want to do, if you can just write this down, it will remind you what to do, first of all. Find, that little statement says find del f, find del g. Do you remember what del f is? So let's write that down. Del f is partial of f with respect to x times I. In other words, the partial with respect of f with respect to x is the first component of del f. It's a vector plus what? F sub y j. That's if it's in the plane. Later on, we'll take it to space, right? And then likewise for del g. Del g is going to be g sub xi, partial of g with respect to x, plus partial of g with respect to y times j. We'll multiply that times lambda, and then we're going to set corresponding coefficients equal, which give us a system of equations, the solutions to which represent our critical points that we're interested in. So let's go through this. Let's find del f. Okay, so del f, focus on the given function. Help me out here. What's del f? What's the partial with respect to x? Well, 4x, right? 4x plus 1, right? So let's write it out as a vector. I like to use ij form. You don't have to. You could use component form. So del f equals 4x plus 1i so far. And then plus, okay, the j component is the partial with respect to y. What is that going to be? Just 2y and then times j. Everybody with me? Okay, del g. Let's find del g and then we'll multiply by lambda. So del g, okay, this guy, focus on this guy, the left-hand side of this equation. What's the partial with respect to x? So I'm going to leave a little space between the 2 and the x. 2x, 2 space I, 2 space xi. Okay, plus, what's the partial with respect to y? 2 space y j. Why did I do that? Because I'm going to throw in the lambda now. I'm going to multiply by lambda. Could you do that all at once? Most certainly. Does everybody see? All I did was compute del F and lambda del G. Okay, the solutions to the corresponding system of equations that you get when you set the corresponding components equal, those are the critical points we're looking for. So let's set up our system then. We're going to get what? Yeah, I need to keep shrinking this so I can keep everything in sight and not scroll down too much. So we get 4. So I'm going to set this guy 4x plus 1 equal to 2 lambda x, corresponding components. So 4x plus 1 equals 2 lambda x. And what's the other one? 2y equals 2 lambda y. So 2y equals 2 lambda y. There's one other equation. 2y equals 2 lambda y. There's one other equation we can make use of, which is the constraint equation. I usually put in the original form of the constraint, x squared plus y squared equals 4. So write that down as well. Or x squared plus y squared minus 4 equals 0. Either one is true. This, in this box, this is a system of equations. You've got 3 equations and 3 unknowns, right? Lambda is an unknown. You don't necessarily care about lambda. It's a means to an end. If you need to solve for lambda, you're going to use it to get x and y, hopefully. Okay? But it is a means to an end. So the method is to solve that system, come up with your critical points, plug into F. Whichever critical point yields the biggest value, that z value is your maximum, absolute. And the smallest value is going to be your minimum. So, well, it's not always true. I made sure of it, though. The way I can make sure of it is, what does this guy graph to be in the plane? Circle radius 2. It's a closed, in the plane, it's a closed figure, right? You're gonna look at the extreme value theorem in 14.7, but when you're dealing with a bounded closed set like that, you're going to be guaranteed of the existence of extremum if you restrict your domain to that set. It's called the extreme value theorem. But that's how I created these problems, to make sure that these problems would have solutions, basically. So you solve these. That's the hard part. Sometimes it's easy, sometimes it's hard. The reason why it's hard sometimes is these are not, well, they're not all linear equations, right? That third constraint equation, x squared plus y squared equals 4, nonlinear. If you've ever tried solving systems of nonlinear equations, it's a lot harder than solving systems of linear equations. Sometimes you have to get clever with it. Here, I'm going to show you pretty much standard techniques. So I'm looking at this second equation here. First of all, is it okay to divide out constants? It's always okay to divide by a constant, which gives you y equals lambda y. What is not okay necessarily? Dividing by y would be a bad thing. You might say, well, we get lambda equals 1 if we do that. Okay, but then you lose a solution of 0, perhaps, right? So remember, the technique is to set it equal to 0 and factor. Now, there will be times when you know that you're not interested in 0 as a solution. And if that's the case, then you can divide by the variable. But that's not the case here. We're interested in y equals 0. So what I would do from this is I would go ahead and subtract lambda y from both sides, set it equal to 0, in other words. And then what do we can pull out a factor of y, can't we? And then what's left if we do that? 1 minus lambda. And then you guys know what to do from here. You set both factors equal to 0, right? So if we set both factors equal to 0, we get y equals 0. In fact, I'll move it over here. If we set both factors equal to 0, we get y equals 0 or lambda equals 1. And we're going to take these on a case-by-case basis. There's 2 cases. Either y equals 0 or lambda equals 1. There's no getting around that. So let's assume case 1. Let's assume, going up here, so if y equals 0, so we're going to assume this, okay? And then after that, we'll see what happens if lambda equals 1. If y equals 0, go back and look at your system of equations in the box. Is there another one that you could plug into and maybe get x? If y equals 0, that last constraint equation, you can solve for x, right? So let's do it. So we get x squared plus 0 squared, just to be complete. You don't have to write that yourself. Equals 4. Does everybody see where I'm plugging into this third equation right there? And so if x squared equals 4, what does x equal? Well, there's a couple possibilities, plus or minus 2, right? So we just found our first critical points. What are they? Yeah, you could write it all in one. You might have to separate them later on, but plus or minus 2, 0. There's really two critical points there, right? So let's circle that so we don't forget it, because we're not done yet, but we're definitely going to plug both of those into the function to see if they yield extrema. What's the other situation? We could have the case where lambda equals 1. Okay, so if lambda equals 1, go back to your system of equations. Which equation haven't we taken advantage of yet? That top one in the box, right? So let's go ahead and fill in lambda equals 1. That gives us 4x plus 1 equals 4x plus 1 just equals 2x, right? And then, oh, that's easy enough to solve, isn't it? So what does x equal? 2x, negative 1. 2x equals negative 1 at first, and then x equals negative 1/2, as you said. Everybody buy that? Do you notice how I'm done with lambda. I don't care about lambda. Lambda is a means to an end, and I'm done with it. What can I do with that negative 1/2? Plug it into the third equation that involves just x and y, right? X squared and y squared. So if I do that, I'll plug back into this third equation. And if I plug in negative 1/2 and square it, I'll get, what, 1/4? Plus y squared equals 4. So that's going to be y squared equals 4 minus 1/4 if I isolate y squared. Does everybody see that? 4 is really 16/4. So I get y squared is equal to 15/4, or y is equal to? Okay, so plus or minus root 15 over 2. So what are the critical values that I get from lambda equal to 1, that case? So the critical values would be, going up here, negative 1/2, comma, plus or minus root 15 over 2. Okay, I'm going to circle that. Those are two more critical, I call them critical values. Critical points is what they are, right? I've exhausted all the possibilities, you guys. There's only two cases, y equals 0 or lambda equals 1. I looked at all the possibilities in both cases. I've found my critical points. So here's what I want to do. I'll bet I can shrink all of this and you guys will still be able to see it. Okay. So now we'll have enough room to finish without scrolling down. So make a table if you like. What kind of table? Well, really it's, if you make the left-hand side of the table ordered pairs, so we'll call them CPs for critical points. That's what we're going to plug in, and then F of, being a bit liberal with the notation, F of the CPs, right? So what are the CPs? Well, we better separate the plus or minus x one. So we have plus or minus 2, 0. We better separate that to negative 2, 0, and positive 2, 0. Do you see why? If you go back, we're going to be plugging these values into the original function, f. There's an x to the first power there, right? So that negative from that particular term is going to stick around. It's not going to be multiplied out. So you better separate those. And then I don't think for the ones involving plus or minus 15 root over 2, I don't need to separate those, because if you look, f has just one factor of y squared. The negative is going to square out. So I'll do that one all at once. If you want to, if you're not sure, separate it. But I'm saying, okay, we've got two more critical values, -1 plus or minus root 15 over 2 is the y value of that critical value. I plug that in here. Does the negative matter? No, I can do that one all at once. Save a little bit of time. Okay. So is everybody with me so far? Look at the function values. Whichever one's the biggest is your absolute max on the constraint. Whichever one's the smallest is your absolute min. Okay, so let's do that. So let's plug in f of -2, 0. Again, focus your eyes on this formula. So what are we going to get? If we plug in a -2 for x squared, that'll be 4 times 2. What's that, 8? Minus 2. 0 squared is 0 minus 2. What does that get me? 4. So I get a function value of 4 for that one. Now, what if I make it +2, 0? I still get 8 here, but then I get +2 and then a -2. Did I do that wrong? Oh, so let's try that again. How did I get that? Was I thinking ahead? Yeah. Sometimes I think ahead. Okay, so 8 for this one, right? And then a +2, which is 10. Duh. Okay, and then a -2. So what do we get? 8. Okay? Now let's do the last two all at once. And plug in f of -1/2. And then plus or minus root 15/2. Again, the reason I can do this is all I see is a y squared. So the plus or minus root 15/2 is a y value. That negative is going to go away. Either way, you're going to get the same value, in other words, for both critical points. Okay, so what do you get? 2 times 1/4, because you're plugging in -1/2 for x. So 2 times, yeah, let's just go right to 1/2. And then plus -1/2, that's nice, when you plug in right here. Plus, okay, y squared, either way you do it, plus or minus root 15/2 turns out to be 15/4, and then -2. So that would be 8/4, 15/4 minus 8/4, 7/4. Everybody agree with that? Okay. Which one's the biggest? Here's your absolute maximum. Which one's the smallest? 7/4. Absolute minimum.